Now let's take a look at how fast gases are moving by looking at molecular speed. All right, so when I look at molecular speed, I can look at things like kinetic energy, and I can get some relationships between R and temperature. And so remember, we talked a little bit about the correlation between speed and temperature. All right, and then I can look at how much I have there. Kinetic energy, I also have that 1/2 mass times velocity squared. Now, if you look at this though, I've got a really interesting, instead of a normal velocity, I've got that U there. And if we look down here, I get this equation right here. This U is equal to 3RT over M and the square root of that. Okay, well, what is U? U is what we call the RMS, or the root mean square speed of our gas. And so if I take 3 times R times temperature divided by the molar mass, take the square root of that, that's my root mean square speed. Now, we've only dealt with 2 R's so far, but we actually have a third, okay? So if you notice here, I have another value for R. Okay, I have this value for R that's 3.14 joules per mole Kelvin. So we're still dealing with Kelvin for temperature, but now I have joules. And so there's some interesting ramifications of the fact that joules exist in this particular R value. Okay, so joules, if you recall, maybe, a joule is equal to a kilogram meter squared second squared. Okay. The kilogram is what's important here. Now, normally our molar mass is grams per mole, but because we have kilograms in our joules unit, what this means is therefore molar mass needs to be in kilograms per mole. So when we're dealing with this RMS, this root mean square speed, we have to put our molar masses in kilograms per mole, okay? Now I can look at some various different graphs and I can see, distribution of speeds at temperatures. And so at higher temperature, I've got a, wider variety of speeds. And so you can see the higher the temperature, the faster the most probable speed is. I can look at molar mass, and so my lighter, smaller molar masses like helium, or not helium, hydrogen, well, and then helium, but my smallest one, hydrogen, all right, I'm going to get, the greatest potential speed there at that smaller molar mass. Okay, and so we get all those relationships. Now, because we have some equations, we can do some more math. All right, so I've got oxygen molecules. I want to know my root mean square speed of these oxygen molecules. So we're dealing with oxygen molecules, and so we know oxygen exists as O2. So my molar mass of O2 is 32 grams per mole. But remember, because of that R value having kilograms in it, R is in terms with joules. Therefore, molar mass has to be in that kilograms. So I'm going to get 0.032 kilograms per mole. Okay? All right. So we're going to use R is 8.314. Okay. And then we're going to get our temperature is 25 degrees Celsius, which is our 298.15 Kelvin. And then our molar mass was 0.032 kilograms per mole. Okay. All right, are we so far so good? Okay. So we're going to do 3 times our 8.314 times our 298 over our 0.032. We're going to take the square root of that. We're going to get 482 meters per second. Okay, so I stripped out the units there because I wanted to make sure I had enough room to write everything. So remember, this was joules per mole Kelvin, okay? And then my joule was the kilogram meter squared second squared, okay? And so I can do this in terms of my kilogram meter squared over second squared times moles times Kelvin. And so if I put all of that together, all right, so I've got this 8.314, so I get kilograms times meters squared on top. On bottom, I'm going to get second squared times moles times Kelvin. Okay, so far so good. All right, I've got temperature on top, so that was Kelvin. And then on the bottom, I have kilograms over moles. And it's all a square root. So what happens here? Well, my kilograms cancel, my moles cancel, my Kelvin cancels, and then I'm left with the meter squared over second squared. But I take the square root of that, and I get the meters per second. So that's how all the units work out on here. All right, so that's why it's important that we make sure we have our molar mass in terms of kilograms per mole, because otherwise the units aren't going to cancel out properly. All right, now related to this, we have this Graham's law of effusion. So what we're looking at is the rate of effusion is inversely related to the square root of the molar mass. And that makes sense because if we think about like the speed of faster molecules versus, or speed of faster molecules, the speed of heavier molecules versus lighter molecules, the rate of effusion would stand to reason that we are looking at a relationship with that molar mass. Okay, and so we get the rate of gas, so I can do a ratio. So the rate of gas 1 to the rate of gas 2 is equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. Okay. So I want to know the ratio of the effusion rates of helium and methane. So helium is not 44. I can always tell when I am doing a really long recording session because as I get later in it, I start not being able to read my own handwriting. All right, so I get 4 grams per mole for helium. And methane is 16.042 grams per mole. All right. And so when we look at rate 1 over rate 2, the ratio of that is rate 1 to rate 2. And so we're going to put helium as 1. And methane as 2. Okay, I need some more space to write. So again, we get the rate 1 over rate 2 equal to the square root of the second one over the first one. Okay. All right, so we're going to do the rate of helium to the rate of methane is equal to the 16 for methane over the 4 for helium. And so we're going to get 2. So helium to methane equals 2. So helium will effuse twice as fast as methane. Okay? All right. And then I've got some methane again, and it's going to effuse through a porous barrier in 1.5 minutes. Now, the same conditions, an equal number of molecules of an unknown gas is going to take 4.73 minutes. I want to know what the molar mass of unknown gas is. All right, so when I look at this, my rate of my methane is some sort of number of molecules for 1.5 minutes. Okay, my rate of my unknown gas, same number of molecules in 4.73 minutes. Okay. Now, my rate of methane compared to my rate of my question mark, I can rewrite this like this. Okay. All right, we'll continue solving it on the next slide. So I had rate of methane divided by rate of question mark. So I had X molecules, so X over my 1.50 divided by X over my 4.73. Now, if you remember way back to learning fractions, if I'm dividing fractions, I'm actually multiplying by the reciprocal. So I can do X over 1.50 times 4.73 over X. X on top, X on bottom. They cancel. So I'm going to get 4.73 over 1.50. Okay. Now we did, it's the rate of methane over the rate of question mark. So it's the molar mass of question mark over the molar mass of methane. Okay. All right, so we're going to get 4.73 over 1.50. Now, if I have the square root of something over something, I can distribute, I can split that up, and I can get the square root of one over the square root of the other. So I'm going to get the square root of the question mark over the square root of methane. We used methane in the previous slide. That's that 16.042. Okay. By 2, the division there, I'm going to get 3.153 is equal to the square root of my unknown over the square root of 16. All right, and then I'm going to distribute that out. I'm going to multiply each side by the square root of 16, so I'm going to multiply each side by 4. And so I'm going to get the molar mass of my unknown gas is 159.096 grams per mole. And that's how we deal with our speed and our effusion.